Hi and welcome back to this new video. We will talk about a transient responsive first order circuit, and this will be a design example. We have a RC circuit given here, and there is a switch again which will be closed at time equals 0. There are three resistances, R1, R2 and R3, and one capacitor, and there's also one independent voltage source. The values of these components are not given, so this is actually a design example. And the question here is design the circuit such that the capacitor voltage VC makes the transition from 5 volts to 14 volts in 40 milliseconds. So that's actually the condition here. And we need to assume, or we should assume, that the transition is completed after 5 time constants. That's actually the issue what we have discussed earlier. In engineering, we use this rule to assume that the situation is again settled and in steady state after 5 time constants. So that might be more than 99% of the situation of the final value. And the voltage source VM is 20 volts. That's actually the situation. So how do we start? Let's start maybe this time with a graph. So sketch the situation. So what we have is the voltage, capacitor voltage, the time. So this is given in milliseconds, and this is the capacitor voltage as a function of time in volts. So what's actually required is make the transition from 5 volts to 14 in 40 milliseconds. So actually what we need is we need to reach the 14 volts in 5 tau or 40 milliseconds, and this is actually the point where we reach the 14 volts for the first time, and this will be time 5 tau. So this region, so from 0 to this point, will be 5 tau long. So we will use this information. Now, as we know from the previous examples, for calculating the capacitor voltage as a function of time, we required 3 parameters. These are the initial condition, which is given actually here, and also given in text, 5 volts. The final value, final condition or steady state value is 14, and also the tau. What we have is actually 5 times the tau, so we can easily calculate the value of 1 tau. So let's write it down. So the initial value, we know that is the given as this. It is here 5 volts. The final value or the steady state value is 14, and there is also a situation of 5 tau, which must be equal to 14 milliseconds or 0.04. This will give us that 1 tau is equal to 0.04 divided by 5 will be 8 milliseconds or 0.008 seconds. Okay, so again I will make this very clear. This is the initial value, and it is the final value. I will use this time word final. Okay, let's look at the circuit and determine the components and expression for them using this information. For calculating the situation for initial value, we assume that the circuit is still in its original state, so there is no change in the switch, so the switch is still open. So that is actually for the situation for time less than 0. In that case, the circuit is actually considered by VM R1, R2 and R3, and that is in parallel C. We already assumed also that the capacitor will be an open circuit since the circuit is running for a long time. So actually we measuring the open circuit voltage, and which is the voltage across R3. So let's make this also clear. So for time less than 0, which is the initial condition situation, we have the following. VC is the, or let me draw the circuit again, that will help to clarify the situation. So we have the VM, so the R1 in series with R2, and there is resistor R3 going to ground, and we model, as we discussed also earlier, the capacitor voltage is the open circuit voltage, or the capacitor is modeled as an open connection, which is the situation here. So what we want is, we would like to know the expression for the initial value of the capacitor, which is actually the voltage divided rule here. So R3 divided by R1 plus R2 plus R3 times the voltage Vm. Now let's fill in the given values. This is 5, the left side. The resistors are all unknown, so I will write it down as it is, and we will try to figure out using the other equation we have to set up, and this is 20. So if I simplify this, I can divide by 20, and then I arrange the situation. What I get is the following. I have 1 over 4 is equal to R3 divided by R1 plus R2 plus R3. So if I rearrange this again, I can cross multiply, so I can do 1 times this, R1 plus R2 plus R3 is equal to 4 times R3, and that will give us the following: R1 plus R2 plus R3, that will be 4 times R3. And if I rearrange this again to simplify, I will get R1 plus R2 is equal to 3 times the value of R3. Alright, now let's make this clear by designating this is the formula 1. I will use this in the next part. And if I go to situation for time larger than 0, which is required actually for going to the final value and using the circuit for that. If you have the final value, that means actually the circuit has changed. So the switch is closed. This will be a short circuit, so the R2 is out of the picture. What we have is the Vm in series with R1 and R3. And again, we assume the capacitor is an open circuit since the circuit is running for a long time. Again, the same condition and same assumption. So what we have is, again, the similar circuit. The only difference is the R2 is out of the picture. So what we have is the following. So we have the Vm, and that's just connected to R1, and then R3 going to ground, and again we have the capacitor as an open circuit, which will be modeled in this case, and this is for the steady state value or the final value. Again, we can use the voltage divider rule, the same procedure as we did for the initial value. So what we have is the R3 divided by R1 plus R3 times the Vm. That's actually the situation here. Let's fill in the given values. This was 14, and R3 divided by R1 plus R3 times 20. Now let's simplify this as we did for the first step. I can divide by 20, left part and the right part. So I will get 1 over, or 0.7. That might be also possible. So I will get 0.7 is equal to R3 divided by R1 plus R3. And if I simplify this a little bit further to make the equation usable in the next step, I will have R1 plus R3 will be 10 divided by 7, 10 over 7 times R3. And I can again rearrange this, writing down R1 is equal to 3 over 7 times R3. And it will give us the second equation. I will use this to complete, to find the component values also. What we have is now two equations. If you look at it, we have 3 unknowns, R1, R2, R3. And here we have 2 unknowns. If I fill in, for example, substitute equation 2 in here, I still have 2 unknowns, R2 and R3, so I cannot continue with this situation. So I will have to determine another equation. So that will be our next situation. So that's actually the time constant. So let's look at the time constant. So what's actually the time constant? For time constant, we again use the situation when the switch is closed. So actually it's situation when we have the calculation for the steady state, and we look between the terminals of the capacitor, and again referring to the circuit, the capacitor terminals will see a specific resistance here, and then we assume that all independent sources are turned off, so those are off. This one will be a short circuit. So what we have is the following. I redraw the circuit again to make the situation clear. So what we have is we have a short for the VM, we have our R1, we have our R3, and we have our capacitor, and I will draw this to make sure that we see the terminals. These are the terminals of the capacitor. So if I look to the left and to determine the Thevenin resistance seen by the capacitor, which will give us the time constant, because the time constant is the Thevenin resistance times the capacitor value C. And the Thevenin resistance here is the parallel combination of R1 and R3, which is given as R1 times R3 divided by R1 plus R3. Alright, so we already know the tau, so we can actually use this formula to say 0.008, so that's actually 8 milliseconds for tau, is equal to R1 plus times R3 divided by R1 plus R3 times C. And I will designate this as equation 3. Now what you see is, again, we have an equation with 3 unknowns here. We had an equation also with 2 unknowns here and 3 unknowns here. So actually we have now 4 unknowns, and we have 4 unknowns, and we have 3 equations. So actually we need another equation to develop a unique solution for this example, for this design example. But there are no other equations. So what we should do, or what we can do, is select one of the component values, which is also possible, and then continue calculating the other 3 component values. So most of the time we choose the value of C because it is difficult to arrange a suitable value for that in a practical sense. So I will also do that. So I will take a value for C, and I will continue calculating the rest of the values, R1, R2, and R3. So what I do is I will select a value. So select C is equal to 1 microfarad, that is 10 to the power minus 6 farads. What we have is, now we can use the formulas, the equation we have set up. So I can use the following. I can also use this formula. Let's start with 3. So then we have 0.008 is equal to R1 times R3 divided by R1 plus R3 times 10 to the power minus 6. And if I rearrange this, then I will get R1 times R3 divided by R1 plus R3 will be 8 times 10 to the power 3, or 8,000. That's actually another equation, equation number 4. So what I will do now, because I have now 2 unknowns here, R1 and R3, and an interesting thing is the same unknowns are also here, so I will use these. So I will substitute equation 2 in equation 4, such that there is only one unknown. So I will do that here. So I will substitute. So substitute equation number 2 in 4. What we get is the following. We have 3 divided by 7, because this is the 3 divided by 7 times R3 will be R1, so I will fill in R1. 3 divided by 7 times R1, R3 I mean, times R3 divided by 3 divided by 7 times R3 plus R3 is equal to 8,000. So if I rearrange this, I will get 3 over 7 times R3 squared divided by 10 over 7 times R3 is equal to 8,000. And if I look at this, you can divide 1 R3 in this expression, and you will have also division from these factors. So what you get is in total 0.3 times R3 is equal to 8 times 10 to the power 3. So that will give us R3 is equal to 8,000 divided by 0.3, and that is approximately 26667, so 26.667 kilo ohms. That's actually one of the unknowns. So what the next step is calculating the rest of the unknowns. Because we already know R3, we can now calculate R1, and then after we have the R1 and then R3, we can calculate R2. So that will be also back substitution. I will show this here to make this clear. So what we have is then R1 is actually 3 over 7 times what we have here. So there's 26667, which will give us the value 11,429, which is actually rounded off, so it might be a little bit of error. And then we have the formula above. This one, let's fill in what we have. We have the R1, which is 11,429, so 11,429, plus R2, which is unknown, is equal to 3 times 26,667. So I will get the following, and if I simplify this, I will have is equal to 80,001. So what is the R1? R1 is 80,001 minus 11,429. So that will bring us to the value of R2, which is 68,570 ohms. So I have now all of the component values required for this design. So if I summarize, what we have done is follow the procedure for the initial value and the final value of the capacitor voltage, and also use the time constant to determine to set up the equation number 3. Since we know that we have only 3 equations and 4 unknowns, that means we have to select one of the unknowns. Might be also another resistor, so it doesn't have to be a capacitor, but in practical sense we most of the time use the capacitor. We select the capacitor, so this is 1 microfarad, so I will use that first in this equation, and I will set up a new equation with 2 unknowns, and these 2 unknowns are also another equation, so I will use these 2 equations to determine one of the unknowns, and if I know one of the unknowns, I can back substitute to determine the other unknowns, and I will come up with all of the required component values. And this is actually the design, which is actually a step-by-step procedure, but you have to be very careful and also do this with redrawing the circuit. That will help you in seeing the situation more clearly and more easily. Alright, that is for the design example number 1. We will continue with other example and other design and other topics. So if you have any suggestions or comments, please leave it in the comment section. I will try to answer them as soon as possible.